Everybody, we're getting ready to do lesson 2.1 for pre-calculus math today, part 1. Here's my contact email for course materials. 2.1 part 1 today, 2.1 quadratic functions. We got 62 points here of classwork and 0 points of note-taking, so it will be on your classwork. And I have note-taking guides for your classwork. Contact me for those. Otherwise, just take notes off of either the PowerPoint or the video, depending upon how you're watching this, or a CD if you got a CD. Hello, everybody, and we're getting into our bell work here, teachers. This is today's bell work. You have two problems here to evaluate a function at each value of the independent variable, then simplify for number 1 and number 2. Give your students about 6-7 minutes to do these. Okay, welcome back for our solutions for today's bell work. For number 1 up here, 2x squared minus 3x plus 5. And then we have for f of -1 and f of w plus 2. So f of -1 equals 10. And then f of w plus 2 would equal this situation here, which when you go ahead and square w plus 2, then 3 times w plus 2, you will get 2w squared plus 5w plus 7. And then for number 2, g of -2 is 33. And then g of z minus 2, when you plug that into this function here, get 5 times z minus 2 squared minus 6 times z minus 2 plus 1, which when you simplify, combine like terms, you get 5z squared minus 26z plus 33. Okay, so slide number 1 of our lesson today. The graph of a quadratic function, and to get to that point we have first, let's define a polynomial function. Again, you have descending order of coefficients and exponents here. They descend in their value from left to right, and this would be the standard form of a polynomial function of x in degree n. So your leading degree here will be the degree of the whole polynomial. And then polynomial functions are classified by degree. For instance, polynomial function f of x equals a cannot equal 0. A constant function has degree 0 and is called a constant function. So the definition of a quadratic function, a, b, and c, are real. The function is given by this situation here, ax squared plus bx plus c. This is your standard arrangement for a quadratic function. It's called a quadratic function because it's a square. For instance, the table at right shows the height in feet of a projectile fired from a height of 6 feet. So at time 0 it's fired at 6 feet with an initial velocity of 256 feet per second at any time t in seconds. So instantaneously it's 256 feet per second. A quadratic model for the data in the table is right here. Here is our quadratic function that you derive these values from, this function here. And then our t is up to 16. So it's up to 16, I'm sure it will be seconds, in seconds. And then these are the values that you acquire using this function here. The graph of a quadratic function is a special type of U-shaped curve called a parabola. Parabolas occur in many real-life applications like satellite dishes or flashlight reflectors. All parabolas are symmetric with respect to a line called the axis of symmetry, or simply the axis of the parabola. The point where the axis intersects the parabola is called the vertex of the parabola. So we got a lot of terminology here. This is your classwork sheet, or your note-taking guide. So remember those. Contact me. And then page 4, basic characteristics of quadratic function. Here's a parabola here. Here's your vertex at the minimum, ax squared, and then a is greater than 0. So a in this situation would be positive. And then the min for this one would be 0, 0. And then for this graph here are the characteristics of it. Domain is negative infinity, positive infinity. Here's your domain. Your range is from 0 to infinity. This is your range. Decreasing on negative infinity, 0, so it's going from left to right. And then it increases here from 0 to infinity. It's considered an even function. And the axis of symmetry is x equals 0, so your y-axis is your axis of symmetry, and the relative min or vertex is 0, 0. So in this situation here, a is less than 0, so it points down. So here are the stats for this parabola. Domain is negative infinity, positive infinity. Range goes from negative infinity to 0. Here's our range here is negative infinity to 0. The intercept is 0, 0. Increasing on the negative infinity, 0. So in this part of the parabola is increasing. This part of the parabola would be decreasing. It's an even function. A of s is x equals 0, and then relative min, or rather relative max here, this is a max, is at 0, 0. For the general quadratic form, when a leading coefficient a is positive, the parabola opens up. When a leading coefficient a is negative, the parabola opens down. Like here, opens up. So a is positive. And then when it opens down, a would be negative here. Then when sketching the graph of f of x equals ax squared, it is helpful to use the graph of y equals x squared. Y equals a f of x is a vertical stretch of the graph of y equals f of x when a is less than 1 and then greater than 0. So when a is between 0 and 1, a vertical stretch, meaning that the graph will flatten out. And then the graph of f of x is a vertical shrink of the graph of y equals f of x, noticed in figure 2.1. So for that here, this is x squared here, f of x equals x squared. And then when you put 2 here greater than 1, it shrinks here. The parabola shrinks inward, so it makes it a steeper slope here on your parabola when you put a multiplier out in front of your x squared. They call it a vertical stretch. I've heard them called all kinds of things, but that slope gets steeper is what it amounts to. And then here, when your parabola, this is x squared, and then this is less than 1, so the parabola flattens out. The slope isn't as steep as it would be when your a here is 1. So it flattens out when you get less than 1 and greater than 0. And this explains it here, given by f of x equals ax squared opens, determines how widely the parabola is given. When a is small, the parabola opens more widely, it flattens out more than when a is large. So when a gets larger, like 5x squared, it would be really narrow here, is what it amounts. Okay, going to our first example here. Library parent function, sketch the graph here. So we have negative x squared plus 1. So negative x squared plus 1 is going to open down, and then it's translated up 1 unit here on your y-axis. Your y-intercept here will be 1. And then for x plus 2 squared minus 3, this is in vertex form here. You have a shift here of we have our vertex here to be the negative of 2, and then negative 3 will be our vertexes in vertex form. So it shifts over from the origin to 2 to the left here, and then down 3, negative 2, 3. This will be your vertex here from this situation here. Okay, into our first guided practice here. Describe, sketch the graph, and describe how the graph is related to y equals x squared. So we have this situation here. This is in vertex form. This is in vertex form too. So anyway, for this one here, the graph of negative of x plus 3 squared minus 1 is a reflection in the x-axis, a horizontal shift 3 units to the left, and a vertical shift 1 down. So that would be how that would look. Okay, the graphs of y equals f of x plus or minus c, y equals f of x plus or minus c, and then y equals the negative f of x, and y equals f of negative x are rigid transformations of the graph of y equals f of x. Well, really. So when you have y equals f of x plus or minus c, it's a horizontal shift. When you have x plus or minus c inside parentheses, horizontal. And then when it's f of x, and then outside of the parentheses, plus or minus c, it's a vertical shift. So this is vertical, and then this is horizontal here. And then a y equals a negative f of x. It's a reflection in the x-axis. And then f of negative x inside parentheses will be a reflection. Okay, so getting onward here into our standard form of a quadratic function, we got this situation here. This is written in standard form because it's written in the vertex form of a parabola h and k. Here's our h, here's our k, here's our h, here's our k. So our h will be the negative, rather our x-coordinate for our parabola, the vertex of a parabola will be the negative of h, would be in this situation negative 2, and then our k would be our y coordinate would be negative 3. So in that situation, the standard form quadratic formula, and this is the vertex form. It is in standard form, but it's in vertex form. It's a standard form of vertex form. The graph of f is a parabola whose axis is a vertical line, x equals h, and whose vertex is at the point h and k, where a is greater than 0. The parabola opens upward, and when a is less than 0, the parabola opens downward. So you can tell which way it opens by whatever your h is. In this situation here, it would be positive 1, so it opens upward. Okay, let's get into some of that. Identifying vertex of a quadratic. Here is our quadratic here. Write the quadratic function in standard form by completing the square. Recall that the first step is to factor out any coefficient of x squared that is not 1. So here's our original function, and then group x terms, so 2x squared plus 8x plus 7. That's our first step. And then now we're going to factor out a 2. We need to get rid of this 2. So we have 2 times x squared plus 4x plus 7. Factor 2 terms. Now we need to add and subtract 4 over 2 squared, which is 4. We add that inside of our parentheses there. Within parentheses, complete the square. So we have 2 times x squared plus 4x plus 4. And then 2 times a negative 4, remove this out of the parentheses here, plus 7. Regroup our terms, and then we continue to write our vertex form. 2 times x plus 2 squared minus 1. Right. Okay, so on to slide number 8. From the standard form, you can see that the graph of f is a parabola that opens upwards. Here is our parabola here. 2 is positive, so opens upwards. And with a vertex at negative 2, negative 1. Here's our vertex that we got. from our previous factoring. This corresponds to a left shift of 2 units and a downward shift of 1 unit. So again, there's our vertex after we have factored this out, completing the square here. So y equals 2x squared would be right here. I mean, that's comparing it here to y equals 2x squared. It would go through the origin, and then this is your shift here of 2 units to the left and then 1 unit down. Okay, guided practice number 3 here. And describe the graph of the function and identify the vertex here. Use a graphing utility to verify your results. So I'm not going to put a plot here. We're going to do this analytically here using algebra. Same thing down here for you, independent practice. Do the same thing here. Okay, so for this here is our original. And then this factors easily here. It's a perfect square. X minus 4 squared would be our that. Okay, identify x-intercepts of a quadratic function. Describe the graph of f of x equals negative x squared plus 6x minus 8, and identify any x-intercepts. So for this one here, this is our original function. And then negative x squared minus 6x minus 8, factor out negative 1 out of the x term. So here's our a here, it's negative. So we know this thing's going to go like this. And then we factor a negative 1 out, this x squared minus 6x. Then we group our x terms here. The negative 8 goes outside of the parentheses. So when we have a negative 6 and square it, we get 9. And then we subtract it as well. Factor out negative 1 out of the x terms. Okay, so we still have this here, negative 8. And then because b equals 6, add and subtract, so we did that here. We did that here. 9, negative 9. Here is how we derived 9, is 1/2 of negative 6 squared. And then continuing on here, we get this perfect square inside here. We move our negative 9 out, and we move our negative 1. I mean, negative 1 times our negative 9. Regroup our constants outside the parentheses. So when we do that, we come up with a positive 1 here. We have negative x minus 3 squared plus 1. So here's our vertex form right here. So we know that it's the negative of h and k. So the negative of negative 3 would be positive 3 and then 1. So here's our shift here. 3 to the right and then up 1. And then that is our vertex. And then here are our x-intercepts here. 2, 0, and then 4, 0 here. The x-intercepts are determined as follows. So negative x squared minus 6x plus 8 equals 0. Factor out negative 1. And then negative of x minus 2x minus 4 equals 0. So we factor this into this here. So x minus 2 equals 0, and which x equals 2. So that is one of our intercepts, x-intercepts here. And then same thing with 4. 4 is our other x-intercept, second factor equal to 0. So we use our 0 multiplication property of 0 here. So the x-intercepts again are 2, 0, and 4, 0 for this parabola here. Okay, and exercises here. Describe the graph of the quadratic function, this quadratic here. Identify vertex and the x-intercepts. Use a graphing utility to verify. So graph this to check yourself, but first do it analytically here. So for this one, here's our original here. and then we move our -3 out. We're going to complete the square here. Here's our completed square here, and then we multiply negative times negative here is our a for this situation, 3 plus 1, and then this perfect square, -x plus 1 squared plus 4. So when we have that, when we combine our like terms here, -x plus 1, and then we move inside here our 4, we get this quadratic here, negative of x squared plus 2x minus 3, and then we factor this into x plus 3, and then x minus 1, and then x plus 3, the inside here has to equal 0. So we're going to use our 0 property of multiplication to x plus 3 has to equal 0, so x can equal -3. Then x minus 1 has to equal 0, so x will equal 1. So here are our x-intercepts of this parabola. And our vertex here would be the negative of h, so it would be -1 and then 4 would be our vertex. -1, 4. And then our x-intercepts are -3, 0, and then 1, 0. So -1, 4 would move over 1 unit and then up 4. And then it intercepts our x at -3 and then +1. So that would be what your parabola would look like from this original quadratic up here. And that is your 2.1 part 1. Email me here for materials, note-taking guides, tutoring. Thank you very much.